Hello. In the previous lecture, we proved long division for polynomials. Let me quickly recall what the statement was. So suppose A is an arbitrary unital commutative ring, and I give you two polynomials, f and g, and we assume that leading coefficient of g is actually a unit inside this ring A. Now, in that case, we can run the long division algorithm, get a quotient q and a remainder r, which means that we can write down f as a product of this quotient q by g plus the remainder r. And when we say it's remainder, it means that the degree of r is strictly less than degree of g. Let's point out that this condition for the leading coefficient of g to be a unit is automatically fulfilled if the ring A was a field. For a field, we can always divide an arbitrary polynomial by another non-zero polynomial, because the leading coefficient of every non-zero polynomial is a unit when the ring of coefficients is a field. So we will come back to this property later on. But for now, I want to prove the factor theorem, which is an important application of the long division algorithm. Okay, what is the factor theorem? So the point is that in an arbitrary ring A, if I give you a polynomial f, then this polynomial is going to have a zero if and only if a zero at an element A, if and only if it's a multiple of the factor x minus a. So if and only if it has a factor of x minus a in it. Okay, let's prove this. So we start with a slight generalization of that. We show that for an arbitrary element of this ring, small a, we can divide the polynomial f, again an arbitrary polynomial inside this ring, and the ring of polynomials, we can divide it by x minus a, and the quotient, we have no control, but the remainder would be definitely the value of f at a. Okay, so first we prove this, and then as an immediate corollary, we deduce that if f of a is 0, then this term f of a disappears, and we deduce that f of x is indeed x minus a times some other polynomial. So it has a factor of x minus a in itself. So that's why we call it the factor theorem. And vice versa, if f of x is x minus a times q of x, then by evaluating at x equals to a, we deduce that f of a is 0. Therefore, we deduce the factor theorem, which says that small a is a 0 of this polynomial precisely when f of x is a multiple of x minus a. Okay, so let's see how the proof goes. We start by using the long division. So what we will do, we divide f of x, so we are using long division for the polynomial f of x and x minus a. And notice that the coefficient, the leading coefficient of x minus a is just 1. Here is the leading term, and as you can see, the leading coefficient of this polynomial is just 1. And therefore, we can actually use the long division algorithm. And we deduce that there is a unique quotient q and a unique remainder r, such that these two properties hold. F of x is x minus a times the quotient plus the remainder, and the degree of the remainder is strictly less than degree of x minus a. But degree of x minus a is 1. So this means r should be a constant. So we get that r is a constant, and that means r of x is some element of the ring capital A. So let's call that element C, which means f of x is x minus a times the quotient plus this constant C. Now we can evaluate both sides at a, and then automatically this term disappears, because when I evaluate it at a, I get 0 times, no matter what, we end up getting 0. So we get that C is indeed f of a. Now we go back to the equation that we had. which means f of x, going back to this equation, and we plug in that c is f of a, and we get the desired equality, meaning f of x is x minus a times the quotient q of x plus the value of f at a. Now, automatically, as I've explained already, we deduce that a is a zero of this polynomial f. If this is the case, if a is the zero of such a thing, then that by definition, it means f of a is zero. But we just showed that f of x is x minus a times the quotient plus the value of f at a. So this means we have this quotient, and we can write down f as x minus a times the quotient. And the other way around is rather easier. If f of x is x minus a times some other polynomial, we can evaluate both sides at a, and we deduce that f of a is 0. So overall, we get the factor theorem. It says that those polynomials that have small a as a 0, then they are multiples of x minus a. We can interpret this result, the factor theorem, in terms of the evaluation map. So if let's recall that if I define f phi of a to be the function from a bracket x to a, where we are evaluating a polynomial at a, then the kernel of this evaluation map is precisely the set of polynomials that have a small a as their 0. And we just showed that those guys are multiples of x minus a. So we can interpret the factor theorem in terms of the evaluation map as long as a small a belongs to the ring capital A, the ring of coefficients. So later, we will be discussing the kernel of evaluation map when a small a does not belong to the ring of coefficients. And that's the whole, the tricky part of understanding the image of the evaluation map. Of course, the image of the evaluation map here is precisely A, and what we are getting is that by the first isomorphism theorem, we get that the ring of polynomials a bracket x modeled by the ideal x minus a is always isomorphic to the ring A. Okay, so again, let me write it down. So if I combine it with the first isomorphism theorem, we deduce that this modeled by the ideal x minus a is isomorphic to the ring A. Okay, so let's think of, I mean, you can think about it, why we have this implication, and we will discuss it more in the discussion and problem session. But the factor theorem is an important result. It says that small a that belongs to the ring of coefficients capital A is a 0 of a polynomial in this ring, precisely when the polynomial is a multiple of x minus a. Okay, now let's try to generalize it. So what do I mean by that? Here we were discussing about a single solution. How about I give you multiple solutions? So suppose a1, a2, an are distinct zeros of a polynomial. Can I factor them out one after another? It turns out that we cannot do this in general, but when the ring of coefficients is an integral domain, then we can do it. So the factor theorem holds for every unital commutative ring, but the generalized factor theorem, as we call it, holds only for integral domains. So suppose D is an integral domain. Okay, so it is an integral domain. So suppose that this is the case, and I give you a polynomial with coefficients inside this integral domain, and we are told that this polynomial f has distinct zeros, a1, a2, and an. They are distinct, they are not the same elements. If this happens, then we can write down f as product of these factors, x minus a1 times x minus a2 times x minus an times some other factor. and vice versa. The other direction is rather easy, right? Because if I can write down f as product of these factors times q, then you can plug in a sub i's. You can evaluate, you can substitute a sub i's for x, and then the right-hand side would be automatically 0. That means a sub i's are zeros of f. So knowing that we do have these factors, deducing that a sub i's are zeros is rather easy, but the other way around is the important part. So we are assuming that a sub i's are distinct zeros of f, and we want to show that we can write it as product of these factors x minus a sub i's times some other factor. We proceed by induction on the number n, on the number of distinct zeros of f. If n is 1, which is the induction step, then it is an automatic consequence of the factor theorem. So we are given a single zero, and we want to factor out x minus a1. So the base of induction is precisely the factor theorem. So the factor theorem implies the base of induction. Okay, so we go to the induction step. We go to the induction step, which means what? Which means we are assuming that we know what the situation is when I give you n distinct zeros. Now I give you n plus 1 distinct zeros. So we have one more distinct zeros, and we want to write f as product of the factors x minus a sub i's times some other polynomial. So we start with the first n distinct zeros, and we use the induction hypothesis. So by the induction hypothesis, we can definitely write down f as the factors x minus a1, x minus 2, and x minus a sub n times some other polynomial with coefficients inside the ring capital D. Now we are going to evaluate both sides at a sub n plus 1, the next zero. Because by the assumption a sub n plus 1 is a zero of f, the left-hand side, which is this one, is definitely 0. Now, when I evaluate the right-hand side, I get product of these factors, a sub n plus 1 minus a1, a sub n plus 1 minus a2, and so on. And we notice that all of these factors are non-zero because we assume a sub i's are distinct. So again, these things are non-zero because we know that a sub i's are distinct. So in particular, these guys are not the same as the old ones. So because of this, we know that these guys are distinct. So I have product of these terms that are non-zero times the last one. These products happen to be 0. But we do not have 0 divisors in an integral domain. So if product of bunch of elements is 0 in an integral domain, one of them should be 0. The first n terms are not 0 in the right-hand side. So the last term should be 0. So that's the crucial place where we are using the fact that D is an integral domain. So we deduce that the value of q bar at a sub n plus 1 is 0, which means a sub n plus 1 is a 0 of the binomial q bar. But again, now I can use the factor theorem. So therefore, by the factor theorem, q bar we can factor out x minus a sub n plus 1 from q bar of x. So this means by the factor theorem, I can find some polynomial and write down q bar as a product of x minus the new 0 times qx. Now just plug in this q bar equals to x minus a sub n plus 1 times q of x into this. You see, remember, we used the long division in order to we use the induction hypothesis to get this, that f of x is x minus a1 times x minus a2 x minus an times q bar. Now we found out that q bar itself can be written as x minus a sub n plus 1 times q of x. We plug it in and we get the desired conclusion. So this exactly gives us the induction step, which finishes the proof. So again, the important remark is that the factor theorem is true for an arbitrary unital commutative ring, but the generalized factor theorem is true only for integral domains. It's actually a very good exercise to come up with an example where the generalized factor theorem fails for an arbitrary unital commutative ring. So meaning you should give me some ring which is not an integral domain, of course, and the polynomial where that polynomial has many distinct zeros, and we cannot write the polynomial as product of those distinct zeros and so on. Okay, so try to think about this, and we will discuss this in the discussion and problem session as well. Okay, so now an immediate corollary of this is the following, that if the ring of coefficients is an integral domain, then a polynomial, a non-zero polynomial, cannot have distinct zeros more than the degree of this polynomial. Okay, so you might have heard of this type of thing for complex numbers, that a polynomial of degree n cannot have more than n zeros. The same phenomena is true for an arbitrary integral domain. So if D is an integral domain, then a non-zero polynomial, if D is an integral domain, then a non-zero polynomial cannot have more than the degree of f distinct zeros. So again, this statement is not true when the ring of coefficients is not an integral domain. So in being integral domain is crucial in this corollary as well. Okay, so let's see how the proof goes. So suppose, to the contrary, that we do have distinct zeros, a1, a2, a sub m. They are distinct, but the number of them is actually more than the degree of f, and I want to get a contradiction out of it. So we use the generalized factor theorem. Of course, we have distinct zeros, so that would be our first tool to use. So the generalized factor theorem immediately implies that I can f can be written as product of the factors x minus a sub i's times some other polynomial. So f of x is x minus a sub 1, x minus a sub 2, x minus a sub n times this new polynomial q of x for some polynomial q. Now we are going to compare the degrees of both sides. And we notice that because these are units, the coefficients are units, but all the coefficients of these x's are 1, then we have this property that degree of product is summation of degrees. Again, this is one thing that we discussed in the previous lecture. So degree of f would be degree of the first factor plus the degree of the second factor, and so on till degree of q. Now, degree of x minus a sub I is 1, and there are m of them, so we get that degree of f is m plus degree of q. And notice, because f is non-zero, then q cannot be 0. So degree of q is definitely non-negative integer. So which means m plus degree of q is at least m. But m was supposed to be strictly more than degree of f. Now all together, we are deducing that this number, degree of f, is more than degree of f. And that's a contradiction. So this gives us a contradiction. And that means that we cannot have more than degree of f distinct zeros when the ring of coefficients is an integral domain. Okay, so everything went smoothly. The proofs were not that complicated, but now we get an interesting result, interesting conclusion in classical arithmetics, classical congruence arithmetic. Okay, so let's see what I mean by that. So the conclusion, the interesting application of the generalized factor theorem is the following. So suppose P is a prime number, then the claim is that the polynomial x to power P minus x is equal to the following polynomial, x times x minus 1 times x minus 2 times x minus p minus 1, where in the ring of polynomials with coefficients in z sub p. So the ring of integers modulo p. So in the ring of integers modulo p, the polynomial x to the p minus x is the same as the polynomial x times x minus 1 dot x minus p minus 1. Okay, let's see how the proof goes. So by the Fermat's little theorem, we do know that for every element of the ring z sub p, we have that a to the p is a, or a to the p minus a is 0. So we have this automatically by the Fermat's little theorem. What does that mean in terms of understanding it in terms of zeros? It means every element of z sub p is a 0 of x to the p. This means x to the p minus x. This means x to the p minus x has distinct zeros, 0, 1, p minus 1. So x to power p minus x has p distinct zeros. Okay, and remember, z sub p is an integral domain. In fact, it's a field when p is prime number. Therefore, we can use the generalized factor theorem. By the generalized factor theorem, because 0, 1, p minus 1 are distinct zeros of x to power p minus x, x to power p minus x can be written as x minus 0 times x minus 1 x minus p minus 1 times some other polynomial inside this ring. Okay, we are getting close. We're getting closer to the desired conclusion. Now we are going to compare the degrees of both sides. So the degree of the left-hand side is just p, and the degree of the right-hand side, okay, so we have p factors here. All of them have degree 1. So far we get p, and then degree of q. Okay, so the degree of the left-hand side was p, degree of the right-hand side is p plus degree of q, and that means q is a constant polynomial, is a non-zero constant polynomial. Because degree of q is 0, we deduce that q is a non-zero constant polynomial. And every non-zero element is a unit in z sub p. That means we are getting that x to power p minus x is this non-zero constant times the polynomial x minus x times x minus 1 times x minus p minus 1. Okay, now we are going to compare the leading coefficients of both sides. The leading coefficient of the left-hand side is 1, and the leading coefficient of the right-hand side is c. So this means that the constant c is indeed 1. So going back to this equality, we plug in c equals to 1, and we deduce that x to power p is x to power p minus x is x times x minus 1 x minus p minus 1. Okay, so in order to appreciate this equality a bit better, let's prove Wilson's theorem as an immediate application of this equality. So what is Wilson's theorem in congruence arithmetic? It says that if p is a prime number, then p minus 1 factorial is congruent to -1 mod p. So if p is prime, then p minus 1 factorial is congruent to -1 modulo p. So let's see how the proof goes. So by this result, by the previous theorem, we do know that the polynomial x to power p minus x is the same as the polynomial x times x minus 1 times x minus p minus 1 in what ring? In the ring of polynomials with coefficients in z sub p. Now that these two polynomials are the same, I can compare their coefficients. They should have the same coefficients. Two polynomials are equal if and only if all the corresponding coefficients are the same. So I will pick coefficient of x, and I compare coefficient of x on both sides. So I'm coefficient of x on the left-hand side is just -1. Now let's focus and try to understand what is coefficient of x on the right-hand side. So we do have x over here. So this means I have to focus on the constant term of this guy. The constant term is product of the constant terms, or you can just say I'm evaluating at 0. The constant term of the first parentheses is -1. The second one is -2. The last one is -p-1. So this means that this product, -1 times -2 dot 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 -p-1 is congruent to -1 mod p. Saying that they are equal in the ring of integers modulo p means that these integers are congruent mod p. Okay, but here we have -1. So I can factor out -1 from each one of these parentheses, and I end up getting -1 to power p-1, and the rest would be 1 times 2 times 3 dot 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 p-1, which is the definition of p-1 factorial. So we get that it is -1 to power p-1 times p-1 factorial, and this is congruent to -1 mod p. Now if p is 2, there is nothing to prove. If p is 2, 2 minus 1 factorial is 1, and 1 is congruent to -1 mod 2. So in that case, Wilson's theorem is actually rather easy. So let's focus on the case where p is not 2. And remember, p is a prime number. When it's not 2, it is definitely odd. When it is odd, -1 to power p-1 is just 1, because p-1 would be even, and then -1 to power something even is definitely 1. So going back to this congruence relation that we proved, and plugging in 1 for -1 to power p-1, we get the desired congruence relation. So we get that p-1 factorial is congruent to -1 mod p. You see this kind of developing this abstract setting for ring of binomials. Then we ended up showing that this kind of the same ideas that we had for long division can be worked out in this general setting. We can prove the generalized factor theorem, then immediately deduce this nice relation, combined it with the Fermat's little theorem to deduce this equality of binomials in x to power in the ring of binomials with coefficients in z sub p. We immediately deduced Wilson's theorem. So with classical methods, of course, we could prove this, but it would be a bit more ad hoc and case by case and so on. So I really like this example. Another exercise of the same flavor is the following, that we have already discussed it with binomial expansion. We can deduce that x minus 1 to power p is equal to the x to the p minus 1 as long as p is an odd prime number. The fact that it's odd is not that crucial, but let's say odd prime number in the ring of integers modulo p. Now, what you can do, you can factor out x minus 1, use the fact that when I give you an integral domain like z sub p, the ring of binomials with coefficients inside an integral domain is also an integral domain. So we have cancellation law. Cancel out x minus 1 from both sides of this equality, and from there, you should be able to deduce that p minus 1 choose I is actually congruent to -1 to power I mod p. This is another interesting application of polynomial equations in congruence arithmetic. But let's go back to the evaluation map. Okay, so we want to understand we wanted to understand the image of the evaluation map. We have seen a few examples of this type. So suppose alpha is a 0 of a polynomial. We want to understand the ring structure of the image of phi sub alpha. What can we say about the image of phi sub alpha? By the first isomorphism theorem, we already know that this Q joint with alpha is isomorphic to the ring of polynomials Q bracket X modeled by the kernel of phi sub alpha. So in order to understand the ring structure a bit better, I need to have a solid understanding of the kernel phi sub alpha. And we have already discussed that something is a kernel if and only if it is an ideal of this ring. So this means I need to understand ideals of Q bracket X. What can we say about ideals of ring of polynomials with coefficients inside Q? So that's the next thing that we are going to discuss. So what are ideals of ring of polynomials with coefficients inside Q? In fact, what we will show is that if we start with an arbitrary field and consider the ring of polynomials with coefficients inside this field F, then every ideal is principal. So it has a similarity with ring of integers. So in ring of integers, we showed that every ideal of Z is of the form NZ. So there we relied on a result from group theory, which said that a subgroup of Z, every subgroup of Z is a cyclic subgroup, is of the form NZ for some n. And the proof of this result, if you don't remember, relies on long division, relies on division algorithm for integers. So now here we have a field of, the ring of coefficients is a field. We are considering the ring of polynomials with coefficients inside this field F, and we want to show that every ideal is principal. Again, our tool, the main tool, would be long division, similar to the ring of integers. Let's see how the proof goes. So suppose I is an ideal of this ring, and if it is 0, then there is nothing to show. You see, there is a similarity between this and the case of integers as well. So there, again, we separated the 0 case from non-zero case. But let's come back. If my ideal is 0, I'm done. Let's suppose that it's not 0. That means what? That means when I look at the degree of the functions, I can find some non-zero polynomial inside I, and then I look at the degree of these non-zero polynomials. And by definition, these are going to be non-negative integers. So we end up getting a non-empty subset of non-negative integers. So I'm looking at degrees, possible degrees of elements inside I, only non-zero elements inside I. And what I'm going to do, I'm going to take the minimum of such degrees. We do have such a thing by the well-ordering principle. Okay, so because it's a non-empty subset, I can talk about the minimum of such thing. Okay, so we get that there is a polynomial, let's call it P. We take a polynomial P inside this ideal that has the minimum degree among all non-zero elements of this ideal. So among all the non-zero elements of this ideal, we take the one that has the minimum degree. Now, claim is that the ideal I is actually generated by this polynomial. Every other element of the ideal is a multiple of this polynomial. This is the claim. Let's see how the proof goes. So whenever we have an equality of two sets, we have to show that one of them is a subset of the other one and vice versa. So we start with the easy side. Because P belongs to this ideal, all the multiples of P belong to this ideal. And therefore, the ideal generated by P is definitely a subset of I. Okay, so this one was the easy side. Now let's try to show the non-trivial part of it. Meaning, I pick an arbitrary element F of this ideal I, and what I want to do, I want to show that this arbitrary element should be a multiple of P. Okay, so we take out as much as we can multiples of P from F. What does that mean? This means we divide F by P. Why can we do it? Because when the ring of coefficients is a field, all the non-zero elements are units, and therefore we can do long division, and we can divide f by p. Therefore, there are quotients q and remainder r such that f can be written as p times the quotient plus the remainder. And when we say it's remainder, it means degree of r is strictly less than degree of p. Okay, so that's long division. Now let's see what is the consequence. The consequence is that, okay, remember f, we chose it to be inside the ideal I. P is in the ideal, therefore every multiple of p is also in the ideal. That implies that r, which is the remainder, and that's the difference of f minus the product of p and q, it should be also inside the ideal. So r is an element of the ideal, and the degree of r is strictly less than degree of p. But remember, degree of p was the minimum possible degree among non-zero elements of I. So that immediately implies that r should be the zero polynomial, because if it was not zero, then we had found even smaller degree polynomial, non-zero polynomial inside I. So because it's not possible, the remainder should be zero, but that means f is indeed a multiple of p, and therefore it is in the ideal generated by p. So altogether, we deduce that this ideal I is indeed the principal ideal generated by p. So we showed that every ideal of the ring of binomials with coefficients inside a field f is principal. Okay, so this brings us to the definition of a principal ideal domain. So let's see what is the definition of principal ideal domain. An integral domain is an integral domain D is called a principal ideal domain, and we often abbreviate it and just write down PID. So a principal ideal domain, PID, if every ideal of D is principal. You see, we have already assumed that it's an integral domain. So an integral domain is called a principal ideal domain if every ideal of D is principal. A principal ideal ring is an arbitrary ring with this property that every ideal is principal. Okay, so but in this course we focus on PIDs much more than PIRs. Okay, so an integral domain D is called a principal ideal domain if every ideal is principal. And what we showed so far is that ring of integers and ring of binomials with coefficients inside a field, both of them are PIDs. So both of these are PIDs. Okay, so Z and F bracket X, both of them are PIDs. And now let's go back to the proofs and try to understand them and try to see if we can find the common theme and make it in an abstract form and generalize it. If we go to the proof of integers, so here we used from a result from group theory. We said that every subgroup of Z is indeed cyclic. But the proof of that result actually relies on long division for integers. And the proof of the ring, the factor ring of polynomials with coefficients inside a field is also a PID. That one also relies on long division algorithm for polynomials. So the common theme of the proofs is long division. So it seems that if we have a long division type of result for an integral domain, then we should be able to show that such an integral domain is a PID. And this brings us to the definition of Euclidean domains. So we say an integral domain is a Euclidean domain if we have a type of long division property. What does that mean? What do we expect from long division? So long division is supposed to be like this, that if I give you two elements, I should be able to divide A by B, take out as much as I can multiples of b from a, and I should end up getting a remainder which is smaller than b. So there should be a kind of notion of comparing two elements within that integral domain. If I cannot compare them, I cannot get to something smaller. Okay, so that's the goal. We want to get something smaller. That means I need to have a kind of norm function on this set of integral domains in order to be able to compare them. So, so I have an integral domain D, and I want to compare. An integral domain D is called a Euclidean domain if we have a norm function with the following properties. What is a norm function? Norm function at the moment is a function, we denote it by capital N at the moment, from the ring of, from the integral domain that we are given, from D, to non-negative integers. It is important that the image is something discrete. So it means they are not connected to each other. They get separated from each other, countable and discrete. Let's focus and say it's just positive, non-negative integers. So a function from the ring of from the ring D, from the integral domain D, to non-negative integers with the following properties. So the only element that goes to 0 is supposed to be 0. So only 0 goes to 0. 0 goes to 0, and only 0 goes to 0. So norm of 0 is supposed to be 0, and the only thing that has norm 0 is supposed to be 0. That's the first property. And second, and that's the beef of it, we should be able to divide. What does that mean? Whenever I give you two elements inside this ring, A and B, assuming that B is non-zero, we should be able to divide A by B. That means what? That means we should be able to find a quotient and a remainder. They don't need to be unique. So as long as there are some Q and R with the following properties, we'll be happy. So what? We should be able to divide A by B, which means A should be B times the quotient plus the remainder, and norm of the remainder should be strictly less than norm of B. So in that sense, it's the remainder. I mean, for instance, what are the examples? Ring of integers is a Euclidean domain if I use the long division. And what is my norm function? Norm function just sends every integer to its absolute value. Now, if you think about it, and I encourage you to do, long division implies that ring of integers is indeed a Euclidean domain. For the ring of polynomials with coefficients inside a field, it might seem a bit more tricky. We should definitely use the degree function. But because we want to have this property that norm of 0 polynomial is supposed to be 0, but the degree of 0 polynomial is negative infinity. So in order to bring it to 0, we use this trick and consider a norm of the norm of a polynomial to be, let's say, 2 to power the degree. So that way, if I look at the 0 polynomial, the norm will be 0 if and only if the degree is negative infinity, if and only if the polynomial is 0. So we get this first condition, and the second condition is kind of automatic, again, using long division. So integers and ring of polynomials with coefficients inside a field, both of them are Euclidean domains. Now, in mathematics, we often make things abstract when we see a common pattern, and then we use this common pattern and try to find out the essence of the proof, isolate it, and instead of repeating it in various parts. This is a very good example of such phenomena. So now we see that the same type of proofs that we had for ring of integers and ring of polynomials with coefficients inside a field can be done in this generality. What do I mean by that? We can show that every Euclidean domain is a PID. So that automatically gives us a uniform proof that both ring of integers and ring of polynomials with coefficients inside the field, both of them are PIDs. Okay, so we want to show that every Euclidean domain is a PID. And the idea is similar. So we start with a non-zero ideal, and we try to take the smallest element inside this ideal and show that everything else is a multiple of this smallest element. Okay, let's start the proof. Let's say I is a non-zero ideal. Of course, if it's a zero ideal, then we are fine, we are done. Then we want to compare elements, we have to use the norm function. So among all the non-zero elements of this ideal, I take the one that gives me the minimum norm, the smallest norm. So the minimum norm among all the non-zero elements, norm of all non-zero elements of this ideal. Now, again, the claim is that this ideal is generated by this d-naught, which means it consists of multiples of this d-naught. Again, one side is rather easy. Again, I want to show equality of two sets. That means I have to show that one is subset of the other one and vice versa. And similar to the previous case, one side is rather easier, meaning because d-naught is inside this ideal, automatically all the multiples of d-naught are inside I, and we deduce that the principal ideal generated by d-naught is a subset of I. Next, I want to show that every element of I is a multiple of d-naught. So I pick an arbitrary element, small a, of the ideal I. I'm going to divide a by d-naught, use the property of Euclidean domain, get a quotient q and a remainder r with the following properties. A is d-naught times the quotient plus the remainder, and norm of r is strictly less than norm of d-naught. Okay, so I have this division in the Euclidean domain. So similar to the ring of polynomials, we write down the remainder as a minus this multiple of d-naught. I observe that both a and this multiple of d-naught, both of them are inside this ideal I, and therefore their difference, which is the remainder r, that one is also inside the ideal I. But norm of r is strictly less than norm of d-naught. And d-naught was chosen in a way that norm of d-naught was minimum among norms of these non-zero elements of this ideal. That means r should be 0, because no non-zero element of this ideal can have norm strictly less than norm of d-naught. Now, going back to this equality and plugging in r equals to 0, we deduce that a is indeed a multiple of d-naught, which means it is in the principal ideal generated by d-naught. So altogether, we deduce that I is the principal ideal generated by d-naught. So we see that in every Euclidean domain, we can deduce that every principal ideal, every ideal is principal. So again, in mathematics, we have this, I mean, in general, I believe mathematics is the art of finding patterns. So we find this common pattern in different parts. So here we found out the division algorithm had been used in 2 different places, and then we put it together and extract the essence of a proof. So this way, we can use the same argument in new cases and prove that in certain new rings, we might have the same kind of property. So next, we see such an example. So next, we show that indeed the Gaussian integers form a Euclidean domain, and therefore they are the ring of Gaussian integers is a PID. So that's our next goal. That is what we want to show next. And so maybe it's a good spot to stop. So we will continue in the next lecture.